Hi, my name is Tarik Rashid, and today I'm presenting a new algorithm called Fox algorithm. Fox algorithm is a novel or a new nature-inspired optimization algorithm. It mimics the foraging behavior of fox in nature when hunting prey. Now, the algorithm is designed and developed by Hardi Mohammed and myself, Tarik Rashid, in 2020. Algorithm is based on techniques to measure the distance between the fox and its prey while executing a proper jump. Here in this slide, I'm talking about the life of fox, and then I talk about the algorithm, and then I provide a case study so that to see how this algorithm can be implemented and can be used in real life application, real world application. Now, a fox can live in poor environment that has low production in terms of food. Fox have in two colors, white and red. Fox, two types mainly, Arctic and red fox. Red fox are very common and they live in urban areas in Japan, Canada, Europe, USA, and Australia. The Arctic fox are, the Arctic fox has strong ability to hunt prey either from above or below, whereas the red fox can eat animals and plants. It lives between approximately 2 to 4 years. They live in diverse locations. They can be found in mountains. They can be found in forest, desert, and grassland. Fox can live in, can eat vegetables, frogs, fish, and fruits. However, the Arctic fox can eat lemmings or rats, rodents, and geese. The good thing about the fox that they have intelligent methods to hunt their prey. Red fox behavior in nutshell. When snow covers the ground and snow blocks the sight of the prey, red fox try to search for prey randomly, and then it tries or it finds the prey by hearing ultrasound. And then it takes time to get closer to the prey. So listening to the sound of the prey and the time difference, the red fox can determine the distance between itself and the prey. And once the distance is determined or found or figured out, then they'll make a proper jump to catch the prey. So walking is performed randomly according to the minimum time and best position. The red fox moves randomly to discover prey. It can find prey via hearing ultrasound of the prey. This random walk is mainly utilized for global search or exploration. While searching, fox might hear the sound of the prey. After hearing the sound of the prey, at that time, we can say that the fox is in the exploitation phase, which is a local search. The red fox can hear the ultrasound, so the sound of the prey takes time to reach the red fox. The distance sound travels found by multiplying it by the speed of the sound travel in the air, which is approximately 343 miles per second. And usually this value is static. Therefore, we could use a different method to find the speed of sound travel in the air. The red fox usually tries to move forward towards the prey to decide about its jump so that to catch the prey. The jump depends on the sound takes to catch the prey. Usually, foxes prefer northeast jump, and this depends on the magnetic alignment effect. And if it jumps in that direction or in the northeast direction, then the likelihood of killing the prey is 82%. And if the jump is on the opposite direction or in the opposite direction, the likelihood of killing the prey is 18%. So 2 ways to catch the prey. So this is a basic diagram for the exploration and exploitation. Here is exploration and here is exploitation. While hearing the sound, that means the fox in the exploitation, in the local search. And random walk means exploration. This analogy of 2 objects, the prey and the fox, sends ultrasounds and reflect it, and receiver receives it. So, and then this is the way that how we can calculate the ultrasound sensor, the distance. Now, the flowchart is very basic. So we have initializing population first. We start with initializing population. Then calculate the fitness of each fox or each agent, search agent. R is between 0 and 1, random. So if R is greater than 0.5, you go for exploitation, local search. And if it is smaller than 0.5, then go to exploration. Once we are in the exploitation, if P, another variable, if it is greater, random, this one again, if it's greater than 0.80, yes, we go to northeast jump. The fox will jump northeast, or the fox jump the opposite side. And then we amend the X or the search agent that are beyond the limitation. And then we calculate the fitness and the flowchart or the algorithm terminates once the stop criteria is met. For the exploitation, we have this equations, this one distance sound travel, which is equal to speed sound time, speed sound multiplied by time sound travels. As we said, that sound speed sound could be a value of 343 miles per second, but we use a different method to find it, which is equal to best fox position over time sound travels. And then equation 3, distance between the fox and prey, which is equal to distance sound travel multiplied by 0.5, because 2 ways, so we reduce it to 0.5, half of it, mathematically convenient. And then equation 4, we will found jump of the fox, which is equal to 0.5, okay, multiplied by acceleration times t square. You know, the jump could be up and down. Okay, we have two up and down. So the time during the jump time, we squared for mathematical convenience, you know. So just up and down. And here we have either northeast or the opposite, the jump. Excuse me. So this is the new fox agent position. Will be found either this way, if it's jump northeast, or the opposite, which is equation 6. Exploration, the exploration, that means global search, the time, the average time equals the sum of the times, okay, sum of the times in dimension over the dimension. And A is a parameter whereby the searching performance or over the iteration is reduced. So in other words, when the fox, excuse me, when it finds a prey, so you wouldn't go to search, okay, all the time. So the searching should be reduced over the performance of the searching should be reduced over the iteration. So we'll start with a value could be 2, and then will be reduced over the iteration. And then globally, we can find the new position of the agent or fox in this way. The best agent multiplied by a random number in the dimension and multiplied by average time times the A parameter. So this is the algorithm, pseudocode. I can, you can go through it. It's similar to the flowchart that we had displayed earlier. Performance of this algorithm, you know, it has been tested against IEEE CEC 2019, and also it has been tested against several algorithms, and Fox algorithm perform better. Performance, you know, it has also been used for designing, optimizing pressure vessel design problem, and also economic load dispatch problem. Again, Fox performed better. These are some results. This is also some results to see how statistically our algorithm is doing better. The case study that I'm going to show to you, which is a simple implementation of an example, so that we can implement it step by step. We have fx x1 squared plus x2, and x ranges greater than 0, equal greater than 0, and less equal 12. That's for 2x's, 2 dimensions that we have, x1, x2. You could have as many dimensions as you want, but this is only for learning. So randomly we have agents for foxes, 1, 2, 3, 4, 4. And these are the position, x1, x2, 2, 3, 4, 6, 5, 8, and 10, 12. Square them according to the fitness function, and add them up to the with the next dimension, square them, and you will get the fitness for each fox. So this is the mean, this is the least one, the minimum one, 13, this is the best fox in this iteration, in the first iteration. So the best one, we found it. 2, 3, that's the best one. 2, 3. And best fitness 13. That's best score 13. A, we started with 2, as we say, and jump initialized to 0. C1, 0.18, C2, 82. Minimum average time, and R is 0.6 and P 0.2. That's initialization. So second iteration for the first agent, first Fox, it's position 2 and 3. So we try to find distance sound travel, which is equal to speed sound multiplied by time sound travel. Time sound travel, it's a random number between 0 and 1, and we selected 0.5. Compute the speed of the sound in the step. Speed sound equals to best position, which is the first dimension 2 and second dimension 3. 2 divided by 0.5 and 3 divided by 0.5, you will have 4 and 6. So that's for speed sound. Distance sound travel, again, we multiplied by 0.5 according to the equation that we have. We'll have 2 and 3. In the third step, we try to find the distance between the Fox and its prey, which is equal to distance sound travel multiplied by 0.5. And this is the two distances for dimension 1 and dimension 2. Each one of them divided by 0.5. You'll have 1 and 1.5. Now in equation 4, we try to find the jump. 0.5 multiplied by acceleration times time squared. So this also can be found because we have the time can be time sound travel over the dimension. We have the dimension 2 dimensions that we have, 0.5 divided by 2. So the time is found, and we will divide it by 2 according to the visual that I showed you. You have a distance from prey and the fox, so we take half of it. Therefore, we divide by 2, and then we found the jump here. Once we found the jump, then we will find the next position, or the fox update position for the next iteration. So which is equal to distance fox prey multiplied by jump times C1. So that is the result for the first fox. For the second fox, we do the same. These are the position. We try to find time sound travel, and we gave time sound travel is a random number between 0 and 1. Earlier we took, I think, 0.5 earlier side. Now we change it to 0.4. For each fox is different, or you can have the same, no problem, but it's only for learning. Distance sound travel, again, speed sound travel times time sound, time speed sound travel. Again, equation 2 was found. We found speed sound travel, and then we try to find distance sound travel using this equation. Then it was found. Then we will try to find the distance fox between second fox and the object, the prey. So this is how it falls. We use equation 3. For the jump, equation 4 we use, same thing. And then here, the position of the second fox also updated for the next iteration. That is reduced. Now, third agent, we will do the same. Same equation 1, 2, and then 3, and then 4, and then 5. We get the result for the third. Now, just for learning, the fourth agent, we try to send it to make it less than 0.5. The R is less than 0.5, so that we can go to exploration. Then in this case, we use equation 7, 8, and 9. And we activate these equations. We're starting minimum time 0.2 and A average 1.9 randomly between 0 to 2, so 1.9, but start from 2. This is the equation number 6. We said that we are activating this equation. We need to find this. We have this one, which is 2, 3, the best Fox in first iteration, position 2, 3, and random dimension 1 over from 1 to dimension. We found that random 0.2, and then by the time 0.2 and A is 1.9, we found the 2 position, this 2 multiplied by this, and 3 multiplied by all these. Then we found this one. This is a basic calculation for how to implement the Fox algorithm. You see the new values for second iteration are less, and we can say that this square plus this square, we will find the fitness, and the minimum fitness will be selected. Here, I think according to this might be the minimum, probably, so it depends. So it has to be calculated. And in conclusion, before conclusion, I show you that was the first iteration that we started, and now the value of x1 and x2 have been changed. When you increase the number of search agents, the performance will be better, but then in terms of accuracy, but in terms of time and complexity, you might get the algorithm might get slower. This algorithm is very, very good. It has a very good technique to make a balance between exploration and exploitation. And this new technique of having best balance between exploration and exploitation, which was found in this algorithm in Fox, can be generalized for other algorithms. For the future, we can hybridize, modify this algorithm. We can use multi-objective. We can use real-world application on them. Thank you very much. And if you have any problem, this is the paper that you can go and download it. Again, the pseudocode is in this link. And if you have any problem, you can email me. I can be found in these 2 email addresses. Thank you very much and wish you all the best. Thank you.